Title of talk by Pietro Lenarda, sorry, from IMT Lucca is Phasefield modeling and simulation of damage in a human vertebra after screws fixation.
Okay, thank you very much. I'm a researcher at IMT Lucca in the MUSAM research unit, which is the multi-scale analysis of material directed by Professor Marco Paggi, and I'm happy to present here a joint work between IMT Lucca and the University Campus Biomedico of Rome, in particular the group of Alessio Cizzi, basically. This work will deal with basically fracture mechanics. So actually, I think it's the first talk on solid mechanics today, and in particular of fracture. So fracture mechanics, some motivation. We are working in the framework of variational approach for brittle fracture, in particular phase field approach for brittle fracture. And we will see some biomedical applications applied to the analysis of fracture occurring inside human vertebra after screw fixation. So what we are talking about, some motivation to use phase field approach for brittle fracture. We think that this approach is it's outside theoretical speculation. It is actually mature for technical applications. So the scope of the present work is to investigate the fracture deformation mechanisms and damage evolution inside the human vertebra after incision of pedicle screws under different loading conditions. And this will be a quantitative analysis in terms of fracture pattern, evolution of fracture volume, and most important of all, basically load displacement curves, basically. So what we are talking about, pedicle screws fixation, is basically a surgical procedure made on a certain tract of the spinal column, in which basically inside one or more vertebrae are inserted those kind of implants, so those screws made of titanium alloy, basically. And this is due to basically promote stability of the spinal column, reduce pain, for instance, in the case of discoidal hernia. So here we had, for instance, an intervent of this kind. The diagnosis was of intervertebral disc hernia. And we can see that the first surgical intervention had to be retaken. So the patient felt pain again, so he had to retake a secondary surgical intervention. You can see, for instance, that the position of the screw here is completely asymmetric in the first surgical intervention, and so the screws had to be replaced. Okay, so talking about the phase field formulation for brittle fracture, there is basically a jungle of phase field formulations for brittle fracture. We have many models, for instance, the volumetric deviatoric approach by Amor, the hybrid approach by Laura De Laurentiis, the Royer-Carfagni model. Actually, for this work, the present work, we adopted the spectral model by Mie, which is known to be very robust in terms of fine intelligent implementation. It accounts for damage reversibility and also takes into account the degradation mechanisms, which involves internal stress states of tensile kind, basically. So here what we have, the variational formulation of the problem in the regularized framework. Basically, we have the total potential energy of the system is decomposed in two terms. We have the strain energy density of the material, which is a function of the strain, and this variable S, which is the phase field variable. which is a damage variable taking place between the interval 0, 1. 0 means intact material, and 1 means fully damaged material. And here we have a second integral, which is basically the fracture energy density, in which we can see a constant here, which is the fracture energy of the material, and this gamma function here, which is the so-called crack density functional or Ambrosio-Tortorelli functional, which is a function of the phase field variable, so the damage variable and its gradient, basically. This approach is called regularized because via gamma convergence, basically. So if we let this L, which is basically the main character of the story, the internal length scale of the fracture, if we let this L go into 0, basically via gamma convergence, it is proven that this functional here converges to a discontinuity in which the integral over omega is replaced on an integral of the effective discontinuity, so the crack inside the material, basically. Okay. What about the Cauchy stress tensor? We have that the damage variable, the damage function here is associated to the tensile part of the Cauchy stress tensor, and we can see here that these plus and minus here involving the strains are basically the spectral decomposition of the strain. So that's the reason why this model is called spectral model. And we can see that in this model, the damage mechanism is activated by internal stress states of tensile kind, basically. Okay, so what about the solution scheme? We adopted a staggered solution scheme. Why a staggered solution scheme? Because it is known that the monolithic approach has a functional which is not convex in general, while the convexity is obtained considering two sub-functionals, basically one for just the mechanical problem in which the phase field damage variable is freeze, and then we solve the problem for the phase field variable, which is of basically Poisson type of equation, so it is known to be convex. So alternating those two those two variational problems, we find basically our solution, which is in terms of U and S. Here, I just want to mention that the mechanical problem here is nonlinear due to the spectral decomposition of the Mie model. So we had to employ a Newton-Raphson solver to solve this. And this is done basically using the symbolic derivative, which is available in the software with finite elements Phoenix, basically. For what basically regards the phase field equation, so the evolution of the damage, we have this variational problem here, and we can see that okay, this is a sort of diffusive part here. We can see that involves the gradients, and this is basically this H here, which is the source of damage, basically, is the so-called strain history function of, or crack driving force, basically, is a source of damage, basically, and is coupled with the internal strain of the material, and this accounts for the irreversibility of the crack. Of course, the crack can only advance, basically, inside the material. Okay, so basically, this is the staggered solution scheme that we adopted. First, we solved the mechanical problem where the phase field variable is frozen. Then we evaluate the displacements, and we plug the displacements inside the phase field equation, and we solve for S. and we iterate those two until we reach convergence, basically. So this is a stopping procedure to go to the next loading step, basically. Okay, so going back to the modeling, we have here that this mesh was provided by the Campus Biomedico of Rome after a CT scan from the spinal column of the 49-year-old female patient. This is the L4 lumbar vertebra, basically. And these screws were inserted inside this mesh, having different orientation in terms of these two angles. One is the so-called medial angle, and the other one is the so-called craniocaudal angle with respect to those lines, basically. And regarding the loading condition, we have let's say physiological loading, which is due to the weight of the body, of the upper part of the body, basically of the human being, which is applied on the top of this part of the bone. While to replicate the principal movements which are allowed to the vertebral column, basically we considered three kinds of possible motions, which are basically applied to the to the head of the screws here, which are basically flexion and extension and left and right torsion, basically rotation. Regarding the reconstruction of the Young modulus, this of course is a material which is not uniform, it is a bone. So we have a non-uniform spatial distribution of the Young modulus. And this was obtained by basically the apparent density from the CT scan. And it was reconstructed via interpolation, basically. Regarding the modeling of the screws, they are considered fixed. So there is no sliding or decohesion inside the vertebra, and the screws are modeled basically considering a Young modulus, which is much higher than the rest part of the mesh, basically. This is not a simplified assumption, because actually we know that after the screw insertion inside the human vertebra, after some time the healing process, so this is a living material actually, so there are osteons, there are cells which are basically reconstructing around surrounding the screws and making this fixed with the whole surrounding tissue, basically. So there is no decohesion or sliding of the screws. Okay, the other critical parameters here for the Phasefield modeling of fracture are basically the fractional energy of the material, which is considered with this formula, which is derived from previous work by Professor Yoshiba. And it is considered as a power law of the Young modulus inside the material, so it is again a non-uniform distribution inside the domain. Okay, regarding the high-performance computing, the simulation were basically run on a supercomputer at Nottingham University using MPI, so splitting the problem with 6 cores. And we basically considered meshes in which the number of the degrees of freedom ranges between 600 to 500,000 degrees of freedom. This is a mesh sensitivity analysis in which we considered a loading condition, a flexion loading condition. So the screws are pulled by the heads in this way, and we can see the formation of this kind of spherical region of damage around the end of the screws inside the cortical part of the body, the inner part of the bone. Here we can see that in terms of peak load, we have a convergence in the load displacement curves. We have a displacement increasing the number of degrees of freedom, and this is confirmed also by the computation of the relative error in terms of known values of the peak load done by numerical experimental results of the same loading condition, basically. So we can see this kind of convergence. I want to mention here that it is really difficult to compare with experimental results, because actually there is there are not so many, and there is a lack of. One reason is, of course, that this surgical operation is done while the human being is alive, so it's kind of difficult to have a comparison with the experimental results. But by now, what we can do is to compare with other simulations using other methodologies and so on, and to compare our results with these kind of methodologies. Here we can see a convergence in terms of profiles of the damage at the fixed loading step. We can see that basically if we cut, we can see the convergence. Let's say that of the damage profile in a semicircular region around the end of the screws inside the cortical part of the bone. Let me just talk very briefly about the main character of the story, which is the length scale parameter here, which actually was obtained for this kind of simulation, doing basically a kind of trial and error procedure, because the only known parameter here that we know is the maximum peak load. So basically doing a sort of parametric analysis, we found the L that basically gives the most close value of the peak load to the experimental results. This parameter here can be interpreted in this framework as a structural factor. This is kind of interesting to know, because actually that value, which has been in the end of the day identified as the dimension which is similar to the lamellar length of the bone structure. So it's very close to this value here, which is interesting because the crack initiation happens at the lamellar structure, at the microstructure, basically. This is the analysis for the other loading conditions. So we had the case of extension. So the load was applied to the head of the screws in the upper direction, and we can see a similar evolution of the damage inside the cortical part of the bone, in particular those semi-spherical regions which are increasing inside. And we can also vary the angles of those screw implants, and we can basically measure the load displacement curves for different angles orientation, and also the evolution of the fracture volume inside the bone. This is for what regards the rotation. So applying a displacement here, rotating, basically we can see that the symmetry is some kind broken, because we have here not a symmetric evolution of the damage inside the cortical part of the bone. We can see that the damaged part involves only the head of the screw, at which is basically the direction of rotation, basically. Just to conclude, I want to mention that we also made some modeling of and also characterization of the mechanical failure of this material, which is called bioapatite, and it is an ideal candidate for bone replacement. This is a synthetic material, so it has a porous structure, actually a multi-porous structure, because the porous structure is mesoscale and microscale, actually. And it was tested with at the IMT Lucca for characterizing its mechanical properties. And so the model here was used also to characterize the failure of this porous structure, and to compare it with low displacement curves. We have a paper which is under review here since 1 year, actually. But this is another application of the Phasefield model for brittle fracture, actually. Okay, conclusion, we had a careful assessment of fracture pattern inside the human vertebra after this surgical operation, which is the insertion of pedicle screws. We analyzed the force displacement curves, and we think that this methodology can be used also by, well, can be sold actually to medical doctors to make some prediction analysis before the intervention, before the surgical intervention. And can be beneficial also for the clinical problems. Thank you for your attention. Please.
About your comment that the problem you will not be able to solve because you don't have complex functional. So what are you converging to?
Yeah. No, we are able to solve it monolithically. So we have a solver also for the monolithical problem. The fact is that it's very heavy. So we also compare the solution obtained with the staggered approach with the monolithic, and we have more or less the same. So we are happy of this because, of course, the staggered procedure is much more faster. But actually, we also implemented the solver monolithically. Yeah. The only problem with the monolithical solver is that once you do not converge with the Newton, you are stuck. And there is less, it's less robust in a certain sense with respect to the staggered procedure. When it's staggered procedure, you have two sub-problems which that are, let's say, convex. So if one failed to converge in a certain sense, the other one for sure is converging, because the Phasefield is you have seen it's a Poisson-like equation, so it's very easy by itself to solve it. The problem is the mechanical part.